Hello, and welcome to this lesson in quantitative reasoning. We are talking about sets and Venn diagrams, in the set operations, complement, intersection, and union, and what they look like on a diagram and what they mean. This is the first of two videos in this topic, and it goes along with the videos on just what is a Venn diagram that were previously posted. So, we're going to determine the complement, the intersection, and the union using a diagram. Remember, Venn diagrams are the ways we graph sets. So suppose we have a grouping of distinctly numbered balls where some are green and some are red. So like they're the numbers 1 through 10. Some of them are green and some of them are red, but they all have different numbers. That's what distinctly means. Now we might want to gather together all of the ones which are not red. Well, in the case of gathering together the ones which are not red, that probably means you're picking up the green ones. To do this, we can simply toss all of the balls that are not red into an empty bin and we are done. When you have that bin that is all the balls that are not red, that is the complement of the set of red balls. It is everything you have that is not one of the red balls. That mathematical definition is a little more complex, but that's the idea. It's everything that is not included in the set of red balls. So the complement of a set contains everything that is not in the set. And when we mean everything, we're talking about everything relative to what we're concerned with in the problem, what we call the universal set. So if I were talking about the set of students in a classroom wearing hats, the complement of that set is the students in that classroom not wearing a hat. Not this, I wouldn't have to go looking through the whole school building to find all the elements of the complement, because the universal set I'm talking about in that case is just in that classroom. If I said the students in the building wearing hats is a set, the complement of that would be the students in the entire building who are not wearing hats. That's, in that case, the universal set would be the students in the whole building. So the complement is just everything that's not in the set. And a complement is relative to the universal set. That's what I said. If I gave you a list of numbers, 1, 2, 3, 4, 5, and I said, give me, this is your universal set, and A is the set containing 1, 2, 3. A complement, so I have to go through the universal set, but I have to skip 1, 2, and 3 because they're in A. I just want the things that are in U that are not in A, and that would just be this 4 and the 5. So A plus its complement should give you the universal set if you put them together, if you join them in a union. So A complement here would be 4, 5. Because those are the things that we're considering in this problem. 1, 2, 3, 4, 5 is universal set, so that's what we're considering. And A contains 1, 2, 3. I want to know what did I leave out of A, out of that universal set. So 4 and 5 are the things that are left. All right, so on a Venn diagram, let's see how this looks. We have a universal set of red, orange, yellow, green, blue, and purple. We have set A as red, purple, green. So if I want the complement, I'm going to go through the universal set and cross off anything that is in A. So I cross off red, I cross off green, I cross off purple. So what's left is orange, yellow, blue. If I look at that on a Venn diagram, A is generally represented by a circle. We'll see this in the next slide too. If that's set A, and this out here is the universal set, then a complement will be everything outside of that circle. Oh, I didn't mean to go in the circle. I went in the circle there a little. That's wrong. I got to stay outside the circle, but it'd be everything outside the circle that contains A. So take a look at the next slide. It goes through that again with a different example. So for this example, the universal set is all integers from 1 through 6 inclusively. That means it includes the n's. So the universal set for this one would be 1, 2, 3, 4, 5, 6. And then I need to put my braces at the end. So that would be the universal set, 1 through 6 integers inclusively. A is 2, 3, and 5. So if I want A complement, I cross off the 2, I cross off the 3, I cross off the 5. What they've done in this problem is they've made a Venn diagram, a single set Venn diagram with one circle out of the problem. So you can see the things in A, 2, 3, and 5 are inside of A. And the things that are left, remember when you make a Venn diagram, when you're done, every element in the universal set has to appear once and only once. 1, 2, 3, 4, 5, 6. So the things outside of the Venn diagram, outside of the set A, outside the circle for A, are 1, 4, and 6. So if you make a Venn diagram out of your situation, sometimes it's pretty easy to see what's outside. Or some of you will rather make lists and cross them off. It turns out A complement is 1, 4, 6. Anything that's not in A but is in U. So sets commonly interact. So sets, it's usually not, it's boring to talk about just one set. You talk about two sets and how they overlap and how they join together and things like that mostly. For example, you and a roommate decide to have a house party and you both invite your circle of friends. At this party, two sets of friends are becoming combined, though it might turn out you have some friends that were in both sets, so you might have some of the same friends your roommate has. The set of friends that you both have is called the intersection. So we're going to talk about the intersection of two sets, where the overlap of the sets are, the overlap in two sets is the intersection. So the intersection of two sets, A and B, is a set containing only things that are in both that. It's A and B. They're in A and B. The intersection is noticed with this almost, if you use your imagination, looks like an A and B. And when we go to the logic unit, you're going to see that we do this and is the symbol for and. But, or you can think of it as a staple. You staple together the two papers, they have to be overlapping. I'm trying to think of ways to get you to remember the symbol, though you do get your notes available most of the time. Very helpful if you know these symbols cold without having to look them up. So here's another symbol from very beginning of course. This means X is an element of A intersect B. Or X is in both A and B. So it means that means the same thing. X is an element of A and X is an element of B. Remember that is an element of symbol. So that's the intersection. So I have these two sets. They did not give me two sets. They gave me A and U. That this should say B. So consider the two sets. A is orange, purple, green. B is red, orange, yellow. We want to find A intersect B. What you're looking for is what's in common. What do I see in A that I also see in B? So I see I have the color orange is in both. So I go through A. Orange is in A and orange is in B, so it looks like orange is going to be in my set. Purple is not in B. Green is not in B. And once I've finished going through one set, I don't have to go through the other one because I've checked. I'm looking for things in both. So once I've finished looking at each of the elements in one of the sets, I'm done. So I have the set containing orange is A intersect B, which it says down here. So here's another one. Suppose A is the numbers 5, 6, 8, 3. Notice we don't have to write numbers in order in sets. Remember that. There's no order, doesn't matter. The set 3, 6, 8, 5 would be the same as 5, 6, 8, 3. It would be equivalent, meaning the same size, and equal, meaning the same set. There's some more vocabulary from prior work. 3, 6, 9, 2. Now, one of the things we can look at from prior work is these sets are equivalent because they are the same size. It has nothing to do with this new material we're talking about, really, but it's interesting to note they are equivalent. However, they are not equal because they have some different elements. They both have a 3, but A has an 8 and B does not. So as soon as you find one that's different, they're not equal. But they are equivalent because their cardinal number is the same. They have 4 elements. So find A intersect B by drawing a Venn diagram. So unfortunately, they filled all this in. So you're gonna find A intersect B by drawing the diagram. You draw the two empty circles, and then you look for what's in common. Okay, so 5 is only an A. So you put it out in this part out here. If you put 5 here, I'm going to erase that in a second because it's wrong. It is also in B, so you can't write the 5 there. So let me erase that 5 because it is incorrect. There we go. So you go through, and it's easiest to fill these in by first finding the intersection and filling that in. So I see I have a 6 in A and also a 6 in B, a 3 in A, and also have a 3 in B. So first thing I'm going to do is put in the 3 and the 6. And I put them in the space where they overlap. Now, if I trace my circle for A with my pen here, I will have surrounded the 3 and the 6 and the 5 and the 8. That's the 3 and the 6. If I trace my circle with B, circle B with my pen, I also have surrounded the 3 and the 6. It's in both sets. The overlap, where the two circles are on top of each other, where they share an area. So I do the 3 and the 6. Then I go back to set A. Well, I didn't write down the 5 yet, so I've written those down so I don't write them down again, because remember, in a Venn diagram, each element shows up once. So I have a 5 and an 8 in A. They go out here because they're in A, but not also enclosed in the circle B. And then the 9 and the 2 are out here because they're in B, but not in A. So they're not sharing any area with A. They're not in a space that shares that area. If I'm given this Venn diagram, what if I were given this right here as my problem and was asked to find A intersect B? I would right away look to this overlap area and say, all right, there's my intersection. So the intersection is going to be 3, 6, or 6, 3. Order doesn't matter. All right, so I'm going to wrap up this video here, come back for part 2, where we'll talk about what does the union look like on a Venn diagram, and see you in class.